Okay, with this lesson we're going to start to talk about integration by substitution, or what we also call U substitution. And what this allows us to do is to evaluate integrals that involve function composition. So you could almost say that this is like the chain rule for integrals. And since most functions that we work with are not going to be your basic parent functions, it is essential, the meat and potatoes, or the bread and butter of calculus, is working with the chain rule and also working with U substitution for integrals. So let's take a look at what we have. If you recall from working with derivatives that the derivative of a function composition is f prime of x, f prime of g of x times g prime of x. And since integration is really the reverse process of differentiation, then shouldn't it be true also that the integral of f prime of g of x times g prime of x dx should be f of g of x and then plus or minus a constant. So this is the foundation of what we call U substitution, or integration by substitution. Now what we're going to do mathematically, computationally, to accomplish this is to look at the inside function of the function composition. And in the event that the derivative of the inside function is multiplied on the outside of the function composition, for example, we not only have g of x as the inside function, we also have g prime of x multiplied times f prime of g of x. And when we have that situation, we're going to be able to say, well, that integral is just equal to f of g of x plus c. So again, the way this is done computationally, we'll let u equal g of x. Then we're going to take the derivative of u with respect to x, and that's just g prime of x. Then we're going to solve for du, and there du is called a differential. Now you should note that if du is equal to g prime of x dx, then we have that in our formula there, and we're going to replace that in the original formula, in the original integral, with du. And since g of x we know is u, we can now simplify that whole integral of f prime of g of x times g prime of x dx to just read the integral of f prime of u du. And so what we're asking for there is, with respect to u, what is the function whose derivative is f prime? Well, then that would just be f of u plus c. It doesn't say fu c. It says f of u plus c. Anyway, a little brief humor there. So what we want to do now is to swap out the u. I should say a brief attempt at humor. Whether or not it was funny is another story. So we substitute g of x back in for u, and we end up with f of g of x plus c. So now we have a computational strategy whenever we have an integral that meets those criteria, where you have function composition and where the derivative of the inside function shows up or is multiplied times the function composition on the outside, then we can rewrite that and find the integral of that in terms of function composition. So let's take a look at an example. Okay, so let's say I start with the integral of 2x times the quantity x squared plus 1 to the 4th power. Now I have function composition, and the inside function is x squared plus 1. And furthermore, the derivative of that inside function, which would be 2x, shows up on the outside. And it has to be multiplied times the function composition. So when I have that, I let u equal the inside function. I find the derivative of that, solve that for du, and now I'm ready to go back to the original function, to the original integral actually. Alright, so you see the 2x dx, and that's equal to du, and the x squared plus 1, that's u. So I rewrite as integral of u to the 4th du, and that gives me u to the 5th over 5 plus c. And swapping out the u, I get quantity x squared plus 1 to the 5th over 5 plus c. And that's my final answer.